In this lesson, we're going to look at permutations when objects are identical. So in this first example, this is something we've seen before. It says, how many ways can the word monkey be arranged? And remember, a word doesn't mean, it just means the letters are arranged. It doesn't mean it has to be a real word. So if we look here, we've got 6 different letters to be placed in 6 different spots. So 1, 2, 3, 4, 5, 6. That would be 6 times 5 times 4 times 3 times 2 times 1, which would be the same as saying 6 factorial, right? Making sure we're multiplying those all the way. And 6 factorial is the same as 720 different arrangements. Now when we look at example 2, how many ways can the word butter be arranged? Looks like we're doing the exact same thing, right? That should be 6 factorial. However, when you have a closer look, we have 2 T's. Now if I spell it B-U-T-T-E-R that way, placing the first T here and the second T here, and then spell it again, and switch the 2 T's around, unless I actually label the T's or color the T's or do something, those 2 arrangements are really just the same thing, right? That would normally have been counted twice, which we don't want to do. So how do we get rid of our double counts? Well, 6 factorial, which is what you had at the beginning, and then divide through 2 factorial, those 2 arrangements, the double T's. So make a little note here. This is the double T's, right? And that's eliminating identical arrangements. So go ahead and try this next example, example 3. How many ways can the word Mississippi be arranged? Well, Mississippi has 11 factorial arrangements. But again, how do we deal with all those extra letters? So we've got 4 I's, so that would be 4 factorial for the I's. And then we've got 4 S's, so that would be divide through by 4 factorial for the S's. And then finally, we've got the P's, and there would be 2 factorial for the P's. And like before, when we first were introduced to factorial notation, this is perfectly okay to write down, but it's important that when you put this in your calculator and you do the math, you put those brackets in there. So get in the habit of doing that right when you're writing out the question, so you don't forget to do that when you put it in your calculator. Punching that in, I realized for example 2, sorry, I didn't write the answer there, that was 360. And then for example 3, punching that in, you get 34,650 arrangements. Okay, so just to review, example 1, we have no repeated letters, so 6 factorial is fine, right? But in the word butter, we've got 2 T's and they're identical, so we have to get rid of the double arrangements, the double T's. And then for Mississippi, same idea, and we've got lots more repeated, and they all get placed in the denominator to eliminate those identical arrangements. Example 4 is a different type of question, same idea. Okay, we're not dealing with a word. Okay, it says in the mountainous regions of India, China, Nepal, and Bhutan, it is common to see prayer flags. Each flag is a prayer written on it, and the color used to symbolize different elements: green for water, yellow earth, white air or wind, blue sky or space, and red is fire. How many different arrangements of the same prayer can Dorji make using 9 flags, 1 green, 1 yellow, 2 white, 3 blue, and 2 red? So how is this related to what we were doing? okay, we've got 9 flags, so that would be 9 factorial. Placing those 9 flags in their 9 spots, right? But if we've got identical flags, right, 2 white, you can't place those 2 white and identify them from one another. Same with the 3 blue and the 2 red. So we need to eliminate those identical arrangements. So 2 factorial for the 2 white, 3 factorial for the 3 blue, and 2 factorial for the 2 red. And again, put brackets around those so that when you put this in your calculator, you get the proper answer of 15,120 flags. Okay, go ahead and try example 5. You can hit pause on the video, try it on your own. It says, how many ways can the letters of the word Canada be arranged if the first letter must be an N and the last letter must be a C? Try it first before you see how I do it, because I think you have the tools you need to figure this out. So how do we do that? Well, the word Canada has how many different letters here? Let's put our spaces there. Okay, now they're telling us, and they're taking care of 2 letters for us. They're taking care of the N, and they're taking care of the C. It says N must be the N must be the first letter and C must be the last. So let's place those already. So we've taken care of the C and we've taken care of the N. So don't count those anymore. Okay, they've been placed. I'm actually not going to put them on the top. I'll put them on the bottom because the top we'll use for our values. So there's only one option for the N and only one option for the C. But in these 4 other spots, I've got A, D, A. Okay, so I've got 4 letters left to place there, 3 letters left to place there, 2 and 1. And then we would get 24 ways. But then you're telling me, I can hear you, saying, wait a minute, there are 3 A's in the word Canada. This would be fine if those A's were different letters, but because there are identical objects, we need to get rid of those. Right? So, let's just write that down. How do we get rid of those? Well, that was 24. And get rid of those 3 identical A's. So just divide it by 3 factorial. And instead of having 24 arrangements, it's going down to only 4. So there are 4 ways of arranging the word Canada if using the word, arranging the letters of the word Canada if the N is first and the C is last. Alright, let's take a look at a different looking example. The next couple of examples have to do with pathways. So in example 6, it says Bill lives 7 blocks from Jill as shown in the diagram. How many different routes can he take to her place if he walks only east and north? On the diagram, show the number of pathways at each intersection. The number of pathways at any intersection is the sum of the pathways at the previous intersections. So, a reminder for your cardinal points. We've got north, south, west, and east. So in this case, you can only go north and east. So just wait a minute, don't copy the notes down, and have a look at what we can do in terms of counting. So what does a pathway mean? Well, if Bill's walking to Jill's, he can go this way, and then this way, and that would be considered one pathway. Okay? The other thing he can do is he can go this way and zigzag all the way up. Right? He can go this way, And so these are all the different pathways we're counting. Right? Each of those is a unique pathway. So how can we count all these in an organized way where you don't end up double counting any of them? Well, how many different ways can Bill just get to the first intersection? We can look at that. Well, here there's only one way to get there. And there's only one way to get to this intersection. So that's how we're going to start counting. Okay? How many ways can he take to get to this intersection? Well, he can go this way, and that would be 1. Or he can go this way, and that would be 2. So there's 2 ways to get to this. So you can see how we can break this down a little bit easier, okay, in a little bit better, more organized way. Well, how many ways can it take for him to get to this intersection? Well, before we deal with that one, let's deal with this one here. And again, for that one, there's only one way. That's the only way. If we're only traveling north and east, there's only one way to get there. Okay, so we can put that in. But this other one, I can go, this way is 1, this way is 2, and this way is 3. So there's 3 different ways. Now, you're going to see that this is starting to get a bit trying itself, right? But if you keep going, you should start seeing a pattern. And if you haven't seen the pattern yet, I will point it out to you. So this spot here that I just dotted in, I can see is going to be 6 without actually following any of those spots. What am I looking at? I'm looking at the 2 corner spots and I'm adding them up. If I add those up, they give me 6. Okay, can you see that? Oops. So let's try another one. So if I want to do, this is a 1 here. If I want to do this spot here, I take the 1 in this corner and the 3 in this corner and I add them up. And you get 4 for this spot. So keep going with that. 4 plus 6 would give me 10. Right? This 6 and this 4 would give me a 10 here. This 10 and this 10 would give me a 20 here. And you keep going with that all the way along. Just deleting this to eliminate some of the confusion. Okay, and you can go all the way along. 5 and 10 here gives me 15, and 15 plus 20 gives me 35. So in the end, there are 35 ways for Bill to get to Jill's house. Okay, so that's one way of looking at these types of questions. But you need to notice that pattern in order to make life a little bit easier for you. Okay, so you take the sum of the numbers on the top left and the bottom right corners, and that'll be equal to the number of roots in the top right corner of each block. You might want to add that into your notes here, okay? Okay, let's take a look at B. The pop shop is located on a street corner as shown in the diagram. How many ways can Bill go to Jill's but stopping at the pop shop on his way? So we've got the same diagram. We're still going north and east, but we must stop at that pop shop. How does that change what we were doing in the previous example for A? Well, here we would still have one different ways, or only one way of getting to the pop shop. Here we would have one way of getting to the pop shop, but here we would have 0. There's no way, right, if we're going this way, to get to the pop shop by going past that block. And the same in the north direction, these would be 0s, which means these are all going to be 0s as well. Okay, because that's going past the pop shop. So following the same pattern we did in the previous, 1 and 1 here gives me 2, 2 and 1 is 3, 3 and 1 is 4. I've gotten to the pop shop 4 different ways, but I want to get past there to Jill's. 0 and 4 is 4. Same up here, this is a 0, not a 6. 4 and 0 here is 4. We've got 8. 8 and 4 is 12. So there's 12 ways. Now, you're going to see this type of question in multiple different scenarios. They attach different grids together, but it's always the same principle, okay? So you're following the same ideas regardless of whether or not the grids are attached or overlapped. Alright, let's take a look at the pinball game. Okay, and this pinball game always reminds me of Plinko from The Price is Right, where you put the disc in and then it bounces all the way down and can land in A, B, or C. So it says the diagram below shows a game of chance where a ball is dropped as indicated and eventually comes to a rest in one of the 4 locations labeled A, B, C, or D. The ball is equally likely to go left or right each time it strikes a triangle. We want to determine the total number of paths the ball can take and also the number of the paths to each location. So we're going to do this 2 ways. The first way, you can hit pause on the video and try this on your own, is you're just going to trace with your pen all the different pathways. Okay, follow all the different possible pathways, and there's not that many. It's a small enough setup. And then we're going to use the ideas of Pascal's triangle, and it's the same as what we did on the previous, so adding the numbers and going through the pathways. Okay, so here, if I'm just following with my pen, I can go from this first position all the way down to A in one way, and I can go in this first position all the way to D in one way. So I'm going to do that. Now to get to B, I can go this way, or I can go this way, or I can go this way. So there's 3 different ways, and that's going to be the same as C. So I can start here, I can go that way, or travel all the way across and hit that. So once you get all these different possibilities, what do you do with those numbers? Because they can go into A or B or C or D. If you remember, or means to add. So if you add all those possibilities, 1 plus 3 plus 3 plus 1 gives you 8 different ways. Now if we look at doing this a little bit of a different way, we can look at it in terms of counting. So there's only one way to go down here, right? And that stays the same. And one way to go down here. So A and D, you can see we get the same results. And now we can add them, right? If we add this one plus this one, 1 and 1, that gives me 2. Okay? Add the 1 on the left and on the 1 on the right. 1 and 2 gives us 3. 2 and 1 gives us 3. And you get the same 8 ways. Okay? We can apply these ideas to our next example. I'm going to actually skip example 8 for a minute. That's the same grid type of question that we did at the beginning, and you can see here now there are grids attached. But let's look at the same ideas from example 7 to example 9. It says, how many ways can the word river be found in the array of letters if you start from the top R and move diagonally down to the bottom? So again, if you highlight or trace the paths, you can see I've already laid them out for you, so it's not getting too messy. But use each one of these to find the 6 different ways, and then we'll use the counting method at the end there. So here we've got R-I-V-E-R. If we follow the same direction but stop here, R-I-V-E-R that way. There's another one and another one. So what are the last ones? Right? This way and this way. So those are the 6 different ways. Okay. If we use the counting, right, and then you're adding across. So this would be 2, this would be 3, this would be 3, and 3 plus 3 gives you 6. So whichever method you choose, you'll still get the 6 ways. Okay, I'm gonna actually leave you with this example 8. Try this. Okay, it says Ryan and Patricia leave home and take a taxi to the graduation party. Calculate how many different routes the taxi driver can follow to take them to their party. Assume he can only drive south or east. Okay, so go ahead and try that. I'm gonna put my solution at the end of the video, and then you can see if you get the same answer as me. So hit pause, try it out, and see if you get the number of routes that I get. Okay, so starting at the beginning, at home, we would have 1 through here, and then adding, that would be 2, 3, 4, 5. And usually this first box everyone does okay with. And then it's how do I get from this box to the next one? And you don't necessarily have to. Okay, I'll show you 2 different ways. You can either do each box separate. Oops, that would be 35. So you can stop there and say this one is 35 ways. And then you can do the next box and then the next box and do them each separate. So I'll show you that way first. So if you treat each grid as a separate arrangement, so this would be 4 ways, and then this last one, and then what do you do to get these all put together? Well, it's 35 ways and 4 ways and 10 ways, because we have to get through all of these to get to the graduation party. So you would take 35 multiply by 4 multiply by 10 to give you a total of 1,400 different ways to get from home to the graduation party. Method 1. Method 2, I'm just going to erase this here. If we continued from here, it's 35 different routes to get here. This would be continued with the 35 routes. And then add. Okay, so you keep going, you're just tracing that across. So that's still 35 routes. You're not going any different routes yet. So this would give you 70, 105, 140, and then you take that 140 across. The numbers get bigger, but the method is the same. Hopefully you can read that. 840, this would be 560, 560 plus 840, you still get the 1,400 routes. Okay? And that's it for this lesson. Thanks for joining me.